So when we saw vertical asymptotes, we saw what are called infinite limits, and that's what happens when the y value approaches, say, positive infinity or negative infinity. Here we're going to look at limits at infinity, which now we're going to say rather than having the y value approach positive or negative infinity, we'll say, well, what if the x value approaches positive or negative infinity? What does that look like? So we're just going to take this video to look at some simple functions here and say, well, what is going to happen to our y value as x approaches positive or negative infinity? And we'll work with some simple functions that we know the graphs. We know what they look like, so we can just look at the pictures and hopefully intuit what the limits are. So first thing I want to look at in the first two examples is the limit as x approaches positive infinity or negative infinity of x squared. So if I were to just very quickly look at the graph of y equals x squared, hopefully we remember what that looks like. We know that that is a parabola. So it looks something like this. But when we look at this limit, rather than say, okay, I want to look at the limit as x approaches 1, now we're saying what's happening as x approaches positive infinity. So it doesn't make sense for me to stop at 1 or 2 or 3. Really what we want to say is as we go to as far to the right as possible. So if I were to, you can even start at 0 if you want. If I were to go as far to the right as possible and say, okay, what's my function doing as I move to the right and as I move my way over that way? What is my function doing? Well, in this case, it's going up and up and up and up. My y value is increasing and increasing and increasing. So for the first limit, as x approaches positive infinity, as we move to the right, we see that the y value is also approaching positive infinity here. Now in part B, it's the same function. We're still working with y equals x squared. Oops, y equals x squared. But now we want to say, well, what about as x approaches negative infinity? Here in that case, we're just going in the opposite direction. We're saying, okay, as we move as far to the left as possible, right? Past, say, we want to move past negative 100 or negative 1,000 or negative 1,000,000. We just want to move as far to the right, or excuse me, in this case, as far to the left as we possibly can. And we can sort of extrapolate what our function is doing based on the behavior of this graph. So as I move to the left, as I move further and further to the left, I see in this case, okay, well, my arrow's pointing upward. That means it's just going to keep going up forever and ever and ever, right? I could just keep moving that way, and my y value would just keep going up. So here the y value is increasing and increasing and increasing. That means that this limit must also be positive infinity. So it's all about just what is the y value of the graph doing as we move very far to the right and as we move very far to the left. So let's look at the graph of x cubed next. So here we'll have the graph of x cubed. This graph looks a little bit different. Hopefully we remember it. But if not, our function for x cubed should look something like this. So let's start with part C here. Part C says, what happens as x approaches positive infinity? What's our y value doing? So as we move as far to the right as possible, here our y value is going up and up and up and up and up forever and ever. So our y value is increasing and increasing and increasing. Well, it must go towards positive infinity. Part D, whoops, I've got a typo here. This should say as x approaches negative infinity. So what's happening this time as we move to the left? This time we're seeing something different. We saw kind of really similar behavior in the first three, but here in this example, this time instead of going up, our y value is going down, down, down. It's just going to keep going down. If we were to follow that function, it would just be decreasing forever and ever and ever as we move to the left. So rather than approaching positive infinity, that means that this limit must be negative infinity, since our y value is just decreasing, it's going down, it's going down, it's going down. So it's approaching negative infinity. Next, we've got the reciprocal function. We've got y equals 1 over x. This one's perhaps a little bit trickier. But if I were to graph this function, I would see something like this. Let me do that in a different color. Here's a rough sketch of it. So first thing I want to look at in part E, here, limit as x approaches positive infinity of our function. So what happens as we move very far to the right? So this time around, as we move to the right, we actually see some different behavior here. As we move to the right, it looks like our function is leveling out. It looks like we're starting to kind of flatten that curve, so to speak, right here. And the question I want to ask myself is, because we're talking about limits, I want to know, well, what y value are we getting closer and closer to? In this problem, it looks like it's getting closer and closer to the x-axis, and the x-axis has a y value of 0. It looks like it's getting closer and closer to 0. We actually see a really similar behavior then on the left-hand side. As x approaches negative infinity, again, we're still approaching that red dashed line. We're still approaching the x-axis. So we're still approaching y equals 0. We're just coming at it from the opposite direction. So when we look at these limits at infinity, it's not necessarily going to be the case that our limits are either going to be positive infinity or negative infinity every single time. We can approach a finite value here. We can approach, say, 0 or 5 or 10, just depending on what our function looks like. Lastly, here I've got limit as x approaches positive and negative infinity. Here I've got x to the minus 2. I just want to use my exponent rules to simplify this, get some practice with those. Remember, I can take that negative exponent and make it positive. Say limit as x approaches infinity of 1 over x squared. I think that's much nicer to work with. Now this one is perhaps one that we don't know, so you could take x values and plug them into it, create a table of values, just like we did at the very beginning of this section. I'll go ahead and give the graph to you though, just so that we have something to work with. If I was to sketch the graph of this function, I would see something like this. So for part G, the limit as x approaches positive infinity as I move farther and farther to the right. Again, we actually see kind of the same behavior that we saw in our last function. We're getting closer and closer to the x-axis. Well, I know that the x-axis has a y value of 0, so we're getting closer and closer and closer to y equals 0. The second question to this part then, limit as x approaches negative infinity. Again, we can write that as 1 over x squared if we prefer a positive exponent. This time as we move to the left, again, our function's doing the exact same thing. It's approaching the x-axis, or that red dashed line as I've drawn in there, and that has a y value of 0. So I'll point out here really quickly, the behavior in these last two functions, that red dashed line, that has a special name. It's called a horizontal asymptote. And that's really important. We're going to talk more about that later on in this section. But that's what happens when we approach a finite value. If we approach, say, 0 or 1 or 2, or it could be a negative number. If we approach a finite value, that means we have at positive or negative infinity, that means we have a horizontal asymptote. If we approach, say, negative infinity or positive infinity, like we did up here with these first two functions, then we don't have any vertical asymptotes, or excuse me, horizontal asymptotes. So I want to just really quickly then summarize some of these simple limits at infinity with this theorem here. It says if p is a positive real number, so p has to be a positive real number, and k is just any other number than 0. It doesn't work if it's 0 because then the whole thing is 0, and it doesn't really work out. But if p is a positive number, so that means we're only working with positive exponents. Then we get to say these two things. We get to say the limit as x approaches infinity of k divided by x to the p every single time is 0. So if I wanted to know, say, the limit as x approaches positive infinity of, say, 5 divided by x to the 4th or something like that. Here I've got a positive number, a positive exponent for my variable, and as long as that positive power of x lives in the denominator and x is approaching positive infinity, I get to say that this limit is 0. We don't even need to show any work. That's how nice this is. Same thing for negative infinity. If I wanted to say, look at limit as x approaches negative infinity of, 3 over x to the 10th. You can pick a bigger exponent, but as long as you have a positive power of x in the denominator, and as long as x is approaching positive or negative infinity, then this limit has to be 0. So this is kind of a generalization of those last two functions that we looked at. And I'll point out here that positive exponent is really, really important, because as soon as you start to throw in negative exponents, it makes the function look a little bit different. This theorem sort of falls apart, and we can't use this shortcut. So make sure you're rewriting those with positive exponents before you use this shortcut. The second case is a little bit trickier here. It says if we have k times x to the p, so this time our x to the p power is in our numerator, so this is going to look like the first two functions that we looked at. Here we had, say, like 1x squared or 1x cubed. Then in that case, our limit is either going to be positive or negative infinity. Positive or negative infinity for both sides, for both, as x approaches positive infinity and as x approaches negative infinity. These we don't get to be as definitive on, but we do get to narrow it down to those two options. These will depend on what k is, whether k is positive or negative, and what p is. Is p an odd number or an even number? If we know those pieces of information, then we could say definitively, and we can use what we know about end behavior. But for right now, all we really know is that those limits will either be positive infinity or negative infinity. So for simple limits at infinity like this, we'll be using these two properties quite a bit, and we don't need to show any work if we're going to use them. We can just say, hey, I know this is a theorem. This works for us.